Good evening, I am Lalit Saxena.
I am Ambuja Salgaonkar from University of Mumbai.
Palm leaf manuscripts, as shown in this figure, are age-old documents of social and scientific importance for the data that they hold. Many of them are now brittle, damaged, and the text on them is not very easily readable, and old script readers are scarce.
We have employed image processing techniques including binarization, morphological operations, and similarity-based symbol classification in order to compute damage to the folios, clean up the image, and enhance the readability of the text. Over to degradations and computation of degradation.
A variety of degradation is observed in the manuscript folios. The damage is due to aging, insect attacks, as well as inappropriate storage and handling of the folios. Some such degradations that result in the loss of textual data on the leaf can be seen in the figure. Holes and lost areas are due to termite attack, worn out areas are surface damage due to silverfish attack, and greenish or blackish stains are due to fungi, and finally the areas marked tear and yellow and brittle are the effects of aging.
Computation of damage in the manuscript folios is recommended before handing over the folios to researchers. The damage status report plays a vital role in specifying a manuscript preservation policy.
ASRG is an automated status report generating system that employs binarization for computing the amount of degradation of a given folio. Figure 3 is a snapshot of a manuscript folio by a digital camera, whereas Figure 4 is its binarized image, which serves as the input for computing the degradation.
Binarization is a process of converting a grayscale image into its black and white equivalent. The binary decision about the color of a pixel is dependent of the threshold value. This value can be computed by different methods.
The binarized image has been obtained by adjusting the threshold. Here t is equal to 230 on a grayscale of 0 to 255, using a try and error such that the intensities of both the text and the folio surface are considered black and the background paper on which the folio rests is white. This slide shows a comparison of ASRG output with manually generated reports.
ASRG computes exact areas of the damaged portion and eliminates the effect of stain. This is not possible with the manual method.
Close contact with the manuscripts during manual report generation is hazardous to both the person and the folio. Such contact is kept to the minimal in ASRG. ASRG is eco-friendly, faster, and accurate.
Look at the highlighted cell in the table, that is, computations of the lost area. The bracketed entities U and L in the manual report indicate upper and lower respectively along with the length of the damage. It does not mention the width of the damage, which is significant at the lower portion and much less in the upper right corner.
ASRG reports the exact damage in these circled areas.
Let us move on to the image enhancement. The effect of stains on the readability of the text is clearly visible in Figure 6 at the lower and upper borders as well as holes or perforations all over. The clarity of the image would be improved if we succeed in obtaining black text on a white background. Binarization. A very crude approach is to construct the histogram of the grayscale intensities of the pixels. This is shown in figures 7 and 8. This develops an understanding about the average gray intensity of the text background and that of the text itself. The background is the color of the material on which the writing was done. Valley point in the histogram suggests a threshold that has been applied globally to the folio to get to a binarized form.
Binarization of the folio of figure 6 at t equal to 148 has been shown in figure 9 above. The data that is close to the upper and the lower border is not readable. Clearly, the global threshold did not work satisfactorily at the stained portions. Figure 10 is the result of Savola's binarization method. It shows that thresholding has a better effect in such cases. Savola's formula has been modified in our method. This has resulted in a brighter and more intact impression of the text shown in figure 11.
M is the mean and sigma is the standard deviation of the gray intensities of the pixels in the portion under consideration. The constant of adjustment S takes the value minus 0.5 if the background is dark and plus 0.5 in the case of the other extreme. R is the maximum gray intensity in the picture. Savola has used 148 for his sample. However, manuscripts that are soiled or dust encrusted show a significantly greater value, that is 255 in our samples of Granthascript folios in the library of University of Mumbai.
A domain expert's review of our result has been presented here. In the particular case of figure 6, which is a representative sample of our data, we observed that almost 15% of the symbols deteriorated during image enhancement. This calls for further research.
Interestingly, the reviewer commented that reading a clean folio is faster and that it helps a lot that the digitized form could be read by zooming in. One may please refer to the original image in case of any doubt that may arise regarding the deteriorated symbols.
After folio image enhancement, we attempted symbol classification, which we are going to discuss now. Symbol separation is an essential step in the pre-processing for symbol classification. Granth, not being a continuous script, provides in its standard form the potential for symbol separation by placing vertical lines as a delimiter. However, in the manuscript folios we used, that is not possible as the handwritten letters cannot be expected to be aligned along exact vertical columns that could delimit their boundaries.
We employ the bounding box algorithm to place probable rectangular frames for each of the symbols. A sample result is shown in figure 13.
Symbols are then separated frame-wise. A sample of symbol separation has been shown in figure 14.
One can notice that there are boundary overlaps in figure 13 that have been carried forward into figure 14. Such cases are a challenge in the symbol classification phase that we are going to discuss next.
Morphological operations generally help reducing the noise due to uneven ink impressions in the handwritten text. Dilation is the insertion of pixels at appropriate places that results in the thickening of the symbol, which helps in recreating its shape by recovering broken links. In the other direction, erosion is thinning of the symbol to clearly separate consecutive symbols by increasing the space between them. Skeletonization is the extraction of the essential shape of the symbol by drawing them with one pixel width. Skeletonization improves efficiency and effectiveness of the algorithm.
Figure 11 demonstrates the effect of dilation, erosion and skeletonization on a sample image.
Skeletonized images are then normalized in terms of their size, and a similarity measure based on the correlation coefficient is applied to classify the symbols in groups. A sample classification is displayed in figure 12 here. In a test, we found 266 symbols of Granth folio partitioned into 42 classes when correlation coefficient was set to 0.35.
There are soft computing techniques, a variety of clustering methods in particular, that are more accommodative and self-organizing while grouping the symbols by extracting various features of the script. We believe that further research will reveal a more adaptive grouping algorithm for diverse scripts that are available in manuscript folios. Symbol mapping, a user-friendly interface, is a novel concept that we introduce here in order to further facilitate a novice reader of the script.
Here we present an automatically generated shape-based mnemonic scheme that facilitates reading of Granth script for any user of a Roman alphanumeric script. The sample text of figure 13 and its clean image have been reproduced in figure 16, followed by an automatically generated mapping for the Granth text.
One can see that symbols have been correctly mapped to O and 6. However, the symbols mapping to 7 is not so acceptable. I believe the fourth symbol in the second row should get mapped to D according to this scheme. Accuracy of this mapping would depend on the accuracy of the classification scheme. We are working on it for further improvements.
This example may not be sufficiently convincing for a non-specialist in image processing. The core concept is that once the automatic classification is over, the results will be presented to an expert reader of the script who will supply a suitable transliteration of the symbol for contemporary readers of the script. The text would be then presented to the reader in the transliterated form that would obviously be more user-friendly. For example, Devanagari A will be presented as A and Su would be presented as SU in order to facilitate a Roman script reader.
Here we summarize the contributions of our work on manuscript image processing. ASRG is a low-cost, feasible, and eco-friendly solution for status report generation. It is faster and more accurate than the conventional manual approach.
The digitized images are available in clean form and are widely accessible through ICT. They are more readable images because of their fresh looks and also because the display software supports zoom in.
Generalized techniques for symbol classification does not involve any linguistic resources and hence works irrespective of the script. The user-friendly mapping is a novel concept to utilize the expertise of script readers and facilitate a large number of manuscript researchers who do not know the scripts.
In a more advanced version, one may expect an intelligent system that would keep on building up its symbol mapping tables as and when a new symbol is observed and a mapping is suggested by an expert. Given a user profile, the system would implement a suitable symbol map.
The algorithms and techniques that have been devised through this research have applications in diverse domains. Computation of damage to roads by processing photographs and clarity in the detection of flaws in fabric manufacturing and welding are among the applications of our automatic status report generator. Status reports would be useful in the cost estimation of the repairs in such cases.
Our patent application for ASRG has been published in the Journal of Patent Office of India. We acknowledge the inputs from the number of publications listed here. Thanks, Professor Schroff, for providing us an opportunity to share the findings of our research on image enhancement for palm leaf manuscripts.
We hope that you will find this work interesting, useful, and some amongst you will generate inputs for us to take this work ahead. Thank you.